Welcome back to Mechanical Engineering Made Simple.
It's great to be back.
Today, we're doing something a little different. Usually, we're obsessed with the flashy stuff, We want to talk about rocket nozzles, the aerodynamic curves of a Formula One car.
The shiny exteriors.
Exactly, the stuff that gets all the likes on Instagram. But today, we are going underneath the hood. We're looking at the invisible forces.
The forces that actually determine whether a machine runs for 20 years without a hiccup or whether it explodes in 20 seconds and takes the factory with it.
Right. We are doing a deep dive into what we're calling the 4 pillars of mechanical integrity. Now, looking at the stack of sources we have here, we've got engineering handbooks, white papers on tribology, vibration analysis guides. It's a massive amount of data.
It is.
Our mission today is to sort of synthesize all of this into a comprehensive look at what keeps the world moving.
Or, maybe more accurately, what prevents the world from grinding to a halt. Because that's the natural state of things, right?
Yeah.
Wear, tear, and breakdown. Entropy is always trying to win.
That's a good way to put it. And I want to speak directly to you, the listener, for a second. We know who listens to this. You might be an engineering student, sweating over a board exam, trying to memorize formulas.
Mm-hmm.
Or maybe you're just the kind of person who sits on a plane, looks out at the wing shaking in turbulence, and thinks, how does that aluminum handle millions of cycles without snapping? Or why doesn't my car engine just melt when I'm driving 70 miles per hour?
Yeah, if you've ever wondered about the difference between a machine that feels solid and one that feels, cheap,
Right.
or why some designs last for a century and others fail in a week, this deep dive is for you. We're peeling back the skin of the machine.
So give us the roadmap. How are we going to tackle this beast? Because looking at the source stack, this covers everything from basic physics to quantum level surface chemistry.
And we're breaking it down into 4 specific areas, the pillars. First, we have stress analysis. This is basically the art of not breaking.
Which, looking at the math, is a lot harder than it sounds.
Much harder. Then we move to pillar 2, lubrication, the science of separating surfaces.
Okay.
Then pillar 3, seal technology. Yeah. And it's not just rubber rings, it's about keeping extreme pressure where it belongs.
Right.
And finally, vibration and noise, managing the heartbeat of the machine.
It's a roadmap for mechanical survival. Okay, I'm ready. Let's jump right into pillar number 1, stress analysis.
The foundation of everything. If the structure can't hold the load, nothing else matters. You can have the best engine in the world, but if the frame snaps, you aren't going anywhere.
Okay, so diving into the sources, I hit a snag almost immediately. There's this distinction made between total stress and unit stress. And I have to admit, in casual conversation, if I say stress, I'm thinking about, a heavyweight sitting on a table.
Sure.
But the source material makes a massive deal about this difference.
Yeah.
Why is this distinction so vital?
It's a really common point of confusion, but it's the difference between lay terms and engineering terms. Total stress is simply the total resultant force acting on a section. So let's say you have a bridge column holding up 1 million pounds. The total stress is 1 million pounds.
Okay, that sounds like a lot of stress.
It's a lot of force. But that number 1 million pounds is completely useless to a designer until you know what is holding it up. That's where unit stress comes in. It's the total stress divided by the area, P divided by A.
E over A, the classic formula.
Exactly. Imagine that 1 million pounds is being held up by, a toothpick. The area A is tiny. So when you divide 1 million by that tiny, tiny number, the unit stress is astronomical. The toothpick fails instantly.
Right. It's vaporized. It's not even there anymore.
But now, imagine that same 1 million pounds is held up by a solid concrete pillar that's 10 feet wide. The total stress is the same, 1 million pounds. But the area is huge. So the unit stress, the load per square inch, is actually quite low. Totally manageable. So when engineers talk about stress or yield strength, they almost always mean unit stress. It's a measure of intensity, not just weight.
That clicks. It's about the density of the struggle, so to speak. It's not just about how heavy the burden is. It's about how broad your shoulders are.
That's a perfect analogy, really.
Okay, so the sources then list 3 main flavors of this stress. We hear these terms all the time, but let's define them properly. We have tension, compression, and shear.
The big 3. Tension is pulling apart. Think of a tug-of-war rope. The molecules are literally being stretched away from each other.
Simple enough.
Compression is squeezing, like the legs of your chair right now supporting your body weight. The molecules are being shoved closer together.
And shear. That one always feels a bit more abstract to me.
Shear is sliding. The best way to picture it is with a deck of cards sitting on a table. If you put your hand on the top card and push it forward while the table holds the bottom card still, all the cards in the middle slide past one another.
Okay, I can see that.
That's shear. In the real world, think about a bolt. You have two metal plates bolted together. If you pull the plates in opposite directions, the bolt isn't really being pulled or squeezed, it's being sliced. The plates are trying to, well, decapitate the bolt.
Right.
That's shear stress. It's what happens when you tighten a nut too hard and you strip the threads. You've literally sheared the metal spirals right off the bolt.
Ouch. I've definitely done that. It's that feeling where it gets tight, 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 and then suddenly loose.
And your heart sinks.
Yeah.
Because you just exceeded the shear strength of the steel.
Okay, so we have stress, which is the force applied per unit area.
Yeah.
And then the result of that force, which is strain.
Correct. Stress is the cause, strain is the effect. You apply stress, you get strain. Technically, strain is defined as the deformation per unit length. So it's the change in length divided by the original length.
So if I have a rubber band that's 10 inches long and I stretch it to 11 inches, the strain is that 1 inch of change divided by the 10 inches of original length. So 0.1.
Precisely. It's a dimensionless ratio. And this leads to a really fascinating phenomenon mentioned in our data called Poisson's ratio.
I saw that. It's the idea that when you stretch something, it gets thinner, right? Like pulling a piece of taffy.
Or if you squash it, it gets fatter.
Right.
It's the ratio of the lateral strain, the thinning to the longitudinal strain, the stretching. It's a measure of how much it necks down.
So what's a typical number for that?
Well, most metals, like steel, have a Poisson's ratio of about 0.3.
So it thins out about 30% as much as it stretches. Is that how I should think about it?
Roughly speaking, yes. It has to do with conserving volume, more or less. But look at concrete in the data tables. It has a ratio of only about 0.1.
That's surprisingly low. Why is that?
It is. Concrete is a rigid aggregate structure. It's rocks and sand glued together. It doesn't neck down or thin out nearly as much when you pull on it. Mostly because concrete really, really hates being pulled. It's brittle. It would rather just crack than thin out.
Which brings us to the relationship between the two. We can't talk about stress and strain without talking about the rule that governs them. The sources bring up Hooke's law.
Ah, yes, Hooke's law. It's the rule of linearity. It states that for most materials, up to a certain point, stress is directly proportional to strain.
So if you double the load,
you double the stretch. If you triple the load, you triple the stretch.
It's a straight line on the graph.
A perfect straight line. And the slope of that line, that is a really important number. It's defined by the modulus of elasticity, also known as Young's modulus.
Which is basically a measure of stiffness, right?
Yes, exactly. Think of it as the material's springiness. A high modulus, like for steel, means the line is very steep. It takes a huge amount of stress to create just a tiny bit of strain.
So it's very stiff.
Very stiff. A low modulus, like for rubber, means the line is floppy. You pull it a little, it stretches a lot.
But Hooke's law isn't infinite. That straight line, it breaks down.
Oh, absolutely. It works up to a point we call the proportional limit. Shortly after that, you hit the yield point, and this is the most critical concept for a designer.
Why is that?
Because before the yield point, the material is elastic. If you remove the load, it snaps back to its original shape, just like a spring. No harm done.
But after the yield point,
it becomes plastic. You have permanently deformed it. Think of bending a paperclip. If you bend it just a little, it springs back. That's elastic behavior.
Right.
If you bend it too far, it stays bent. You've passed the yield point. You have permanently rearranged the crystal structure of the metal.
And if I just keep bending it back and forth?
Eventually, you'll reach its ultimate strength. That's the peak of the stress-strain curve. And then, rupture. It breaks.
So for an engineer designing, say, a bridge, the yield point is usually the big red do not cross line.
Usually, yes. If your bridge permanently bends when a truck drives over it, you have failed as a designer. You want the bridge to flex and return, always in that elastic region.
But here is where it gets really interesting for me. The sources go deep into modes of failure. And it turns out, things don't just fail because you pulled them too hard one time. They fail in these sneaky ways.
They do.
And the first one that jumped out at me, and it sounds like a horror movie villain, is fatigue.
Fatigue is the silent killer of machinery. It's absolutely the most common failure mode, and it explains how a material can fail even if the stress is well below that yield point we just talked about.
So I'm not bending the paperclip all the way.
No, you're just bending it a tiny bit, maybe just 10% of its capacity.
Yeah.
But you're doing it 1,000,000 times or 1,000,000,000 times. This is called cyclic loading.
And what's happening inside the metal?
The material gets tired. What's actually happening on a microscopic level is that tiny, tiny cracks form, usually at the surface where there's a little scratch or an imperfection, a stress riser.
And with every cycle,
Mm.
every time the wing flaps.
With every single cycle, that crack opens a nanometer wider. It propagates inward, slowly, quietly. The effective area of the part gets smaller and smaller and smaller until snap, it fails suddenly without any warning.
The data mentions an endurance limit. What's that about?
Yes, this is particularly important for steel. The endurance limit is a theoretical stress level below which you can cycle the material indefinitely, literally forever, and it will never fail from fatigue.
Infinite life. That sounds too good to be true.
Well, it is theoretical, and for some materials, it's not really true. For aluminum, interestingly, it doesn't really have a true endurance limit. Aluminum will eventually fail if you cycle it enough times, no matter how low the stress.
So that airplane wing, it has a finite life.
It has a very carefully calculated and inspected finite life, yes. But for steel, the sources warn us that endurance limit is fragile. Surface condition matters immensely. If the surface is rough or corroded, or if the part is very large, that endurance limit drops significantly.
Because those rough spots are where the microcracks start.
Exactly. They are stress concentrators. A tiny scratch can be the genesis of a catastrophic failure millions of cycles later.
I loved the detail in the source about shot peening. It sounds like a paradox. You blast the surface with little metal balls to make it stronger. That sounds like you're damaging it.
It does seem counterintuitive, doesn't it? You'd think you're just putting a bunch of dents in the surface. But by bombarding the surface with shot, you are actually introducing compressive residual stresses. You are pre-squashing the surface layer.
Okay, so you're squishing the metal on the outside. How does that help?
Well, fatigue cracks need tension to open up. They need to be pulled apart to grow. If the surface is already under tight compression, if it's already squashed together, that compressive layer acts like a shield. The crack can't open. It has to overcome that built-in compression first before it can even start to experience tension. It increases the endurance limit significantly.
That is brilliant. Fighting stress with stress. Okay, so another failure mode, a much slower one, is creep.
Ugh, creep. The slow, permanent deformation of a solid material under a constant stress. We tend to think of metals as solids that hold their shape, but over a long time, especially at high temperatures, they flow.
Like a glacier.
Exactly like a glacier. Or asphalt on a hot day. You know how if you park a car on hot asphalt for a long time, the tires sink in a little? That's creep.
Yeah.
The source material points out the temperature dependence, which is key. Aluminum starts to creep at around 300 degrees Fahrenheit.
That's not that hot. A car engine gets way hotter than that.
Which is why engine design is so tricky. You can't just use standard aluminum alloys for the hottest parts like pistons. Steel, on the other hand, is more robust. It holds out until about 650 degrees Fahrenheit before creep becomes a major issue.
But what about something really hot, like a jet engine?
Right. If you're designing a turbine blade for a jet engine which runs way, way hotter than that, creep is your #1 nightmare. You absolutely do not want your turbine blade slowly stretching out over time and hitting the engine casing.
No, you definitely do not. Okay, then there's impact. This is the difference between placing a weight gently on a table and dropping it.
The dynamic effect. And the math in the source provides a really startling rule of thumb. A suddenly applied load, and this doesn't even mean dropped from a height, just applied instantly, creates double the stress of a static load.
Double, just because it was sudden.
Yes, it's because the material has to absorb the kinetic energy, and that's a minimum. If you drop it from any height, the multiplier becomes huge. This is where the property of resilience comes in, the ability of a material to absorb energy.
And that's related to the stress-strain curve.
It's the area under the elastic portion of the stress-strain curve. A resilient material, like a good spring steel, can absorb a lot of impact energy without permanently deforming. It acts like a shock absorber.
So we have all these ways things can break. How do engineers predict it? The sources list these theories of failure. Why do we need theories? Can't we just, break stuff and see what happens?
We can and we do, but that's expensive and sometimes incredibly dangerous. We need to be able to predict failure before we build, and different materials fail in different ways. The sources highlight 3 main theories.
Let's unpack them. The first one was the maximum stress theory, also called Rankine.
This is the simple one. It basically says failure happens when the principal stress in any one direction hits the ultimate strength of the material. It works pretty well for brittle materials like cast iron or concrete.
Why brittle materials?
Because they don't really stretch or deform, they just snap when the force gets too high in one direction.
But what about for something like steel? That does stretch.
For ductile materials like steel, Rankine is actually dangerous. It doesn't predict failure accurately at all. For that, the gold standard, the one every engineer learns, is the distortion energy theory, or von Mises.
Von Mises. I hear that name all the time in engineering circles. Check the von Mises stress. What is it actually checking?
It's a much more robust theory. It basically says the material doesn't fail just because stress is high in one direction. It fails when the energy used to distort the shape of the material reaches a certain limit.
Distort the shape.
Yeah, to stretch it or shear it. It accounts for the complex interplay of stresses tension in one direction, compression in another, shear all at the same time. It's a much more complete 3D calculation of the stress state.
And the third one, maximum shear theory.
That's the guess theory. It's a little more conservative, a little simpler than von Mises. It assumes failure is caused by the shearing of atomic layers within the material. It's a safe bet for ductile materials if you want to be extra careful, but von Mises is generally more accurate.
Okay, so we have the theories. Now let's look at the shapes, the structural elements. Beams, columns, cylinders.
The building blocks of the mechanical world.
With beams, the source defines this neutral axis. What's going on there?
Right. When you bend a beam, say a simple wooden board across a creek, the top fibers are being squeezed together. That's compression.
Makes sense.
And the bottom fibers are being pulled apart. That's tension. Somewhere in the middle, there has to be a layer that's doing neither. It's not being stretched or compressed.
It's just going along for the ride.
It's just going along for the ride. That's the neutral axis. It's the eye of the storm.
And the stress distribution changes along the beam too, right?
It does. Vertical shear is highest at the supports, where the beam rests on the bank of the creek. But the bending moment, the actual force that's trying to snap the beam, is highest right in the center where you're standing.
Which explains why, if it breaks, it usually snaps in the middle. But if it shears, it would slice off at the edge. Now, columns. This seems straightforward. It's just a vertical beam, right?
You would think so, but columns are dangerous because of completely different failure mode. Buckling.
Buckling.
Yeah. If you have a short, stubby block, it fails by crushing. Simple compression. But a long, skinny column fails by bowing out sideways long before the material itself actually crushes.
I've seen that with a ruler. If you press on the ends, it pops out.
Exactly. The source mentions the slenderness ratio. That's the key metric. It's the length divided by a property called the radius of gyration. The higher that ratio, the skinnier the column, the more likely it is to buckle. Euler's formula is what helps us calculate that critical buckling load.
There's a historical note here that's pretty tragic. The Quebec Bridge collapsed in 1907.
A devastating failure. It was a massive cantilever bridge, and the main compression cords, these huge columns, failed. They buckled. The math they were using at the time just wasn't adequate for structures of that scale.
So what happened after that?
That disaster forced the entire engineering community to rethink how we test and calculate stresses for massive steel columns. They literally had to build full-size replicas of the bridge sections and crush them to understand where the old formulas went wrong.
It's amazing and terrifying how much of our safety rules are written in the debris of past failures.
It's true.
Okay, finally, cylinders. The sources distinguish between thin-walled and thick-walled.
Right. Think of a soda can versus a cannon barrel. In a thin-walled cylinder under pressure, like a boiler or a hydraulic pipe, you have two main stresses to worry about. There's longitudinal stress, trying to stretch the pipe longer.
Okay.
And then there's hoop stress, trying to expand the circumference, make it fatter.
Like the metal hoops on an old wooden barrel. That's where the name comes from.
Exactly. And the math reveals something absolutely critical. The hoop stress is double the longitudinal stress.
Twice as much.
Yes. The force trying to split the pipe open lengthwise is twice as strong as the force trying to pull it apart at the ends. This is why, if you overcook a hot dog, it always splits lengthwise.
Huh. I never thought of that. The hoop stress in the casing is too high.
Precisely. And the source notes that old steam boilers were always double riveted on those longitudinal seams for exactly this reason. You have to reinforce the weak point.
Wow. Okay, so we've analyzed the stress. We know how to keep the machine from breaking apart. Now we need to keep it moving. Let's move to pillar 2, lubrication.
The science of separation. Because if metal touches metal under load, you get friction, welding, tearing, and very rapid destruction. We need a fluid in between.
The sources start by dividing surfaces into conformal and nonconformal. This feels like we're back in geometry class.
It is geometry, but it's geometry with serious consequences. Imagine a journal bearing a shaft spinning inside a bushing. The curve of the shaft matches the curve of the hole. They fit snugly. That's conformal. The load is spread out over a large area.
Okay, and nonconformal?
Think of a ball bearing or gear teeth. You have a sphere touching a flat race, or two curved teeth meeting at one tiny spot. They touch at a single point, or maybe a line.
So the contact area is tiny,
Infinitesimally small.
which means the pressure must be insane.
Enormous.
Yeah.
Absolutely astronomical. And that fundamental difference dictates the type of lubrication you need. We have three regimes. First, the one we always want. Hydrodynamic lubrication.
This is the ideal state, right? The perfect scenario.
It is. Think of water skiing. The motion of the skier creates a wedge of water that lifts them up off the surface. In a journal bearing, the spinning shaft does the same thing. It drags oil into a converging wedge between the shaft and the housing.
And it creates pressure.
It creates a pressure wave that physically licks the shaft completely off the metal.
So it's floating on oil.
Completely separated. It's floating. This is why a properly lubricated engine bearing can last almost forever. In theory, there is zero wear because there is no contact.
But the source notes that the film thickness is significantly affected by load. If you overload it, you sink.
Correct. It's like trying to put a semi-truck on water skis. You're just going to sink. Now, contrast that with the second regime, elastohydrodynamic lubrication, or EHL.
Right.
This is what happens in those non-conformal contacts, the ball bearings and gears we just talked about.
Where the pressure is crazy high.
High. The source mentions pressures over 700 meganewtons per square meter. That is an almost unimaginable crushing force concentrated on a tiny spot.
700. Yeah, that sounds like it would just squeeze the oil out instantly, like stepping on a ketchup packet.
You would think so. Any normal fluid would just be gone. But two things happen. First, the metal itself actually deforms. It dents elastically to make the contact area a little bigger. That's the elasto part.
The steel dents?
It does,
Yeah.
just for a microsecond. But the hydrodynamic part is the real magic. Under that extreme pressure, the viscosity of the oil changes dramatically.
It's thicker.
It gets exponentially thicker. For the split second it's in that high-pressure contact zone, it essentially turns into a solid, becomes glassy. It's hard enough to push the two metal surfaces apart.
That is mind-blowing. The oil turns into a solid shim just when you need it, and then it turns back to a liquid as soon as it leaves the zone.
Physics is handy that way. And what's really interesting is that, unlike hydrodynamic lubrication, the film thickness in EHL is barely affected by load. You can pile on the weight, and that glassy film just holds up.
But then we have the third regime, the one we don't want. Boundary lubrication.
This is what happens when the film breaks down. Maybe the speed is too low to build up a wedge, or the load is too high, or the oil is too thin, the bulk oil is squeezed out.
So the peaks are starting to tug.
The asperity peaks are starting to make contact. Now, you're relying on molecular layers on films that are only 5 to 10 nanometers thick.
We're talking surface chemistry here, not fluid dynamics.
Exactly. This is where oil additives are critical. You have these long-chain molecules that anchor themselves to the metal surfaces like seaweed on a rock, trying desperately to keep the peaks of the metal from actually welding to each other.
Let's talk about the lubricant itself. Viscosity is the big word.
Viscosity is simply the internal friction of the fluid. It's resistance to flow. Think molasses versus water, and the sources distinguish between dynamic viscosity and kinematic viscosity. Kinematic is just the dynamic viscosity divided by the fluid's density.
And we have a choice between grease and oil. Why pick one over the other? It seems like oil is always better.
Not always. Grease is basically oil that's trapped in a thickener like oil held in a sponge. It's great because it stays put, it seals out dirt, you pack a wheel bearing with grease, and it stays there for years. It's simple.
So less maintenance.
Much less. But the source gives a specific warning. The Joule effect limits grease.
The Joule effect, I thought that was about electricity.
In this context, it refers to internal heating from churning. Grease doesn't flow well, so it can't carry away heat. If you run a grease-lubricated bearing too fast, the source gives a speed factor of over 200,000. The churning generates heat that can't escape. The grease literally cooks. It degrades and fails.
So for high speed, you have to use oil.
You need oil. Oil flows, it flushes out contaminants, and crucially, it acts as a coolant. It carries heat away from that critical contact zone.
Okay, so we've analyzed the stress and we've lubricated the moving parts. But a machine is full of fluids. Oil, coolant, compressed air, fuel. We need to keep them where they belong. That brings us to pillar 3, seal technology.
Keeping the pressure in. And we can divide seals into two main camps. Static for parts that don't move relative to each other, and dynamic for parts that do.
Static seems simple enough. Gaskets. It's just a piece of cork or rubber you squash between two pipe flanges.
It seems simple, but there's a real science to the squish. The source introduces two critical factors for gasket design: the M factor and the Y factor.
M and Y.
The Y factor is the seating stress. It's the minimum pressure you need to apply to smash the gasket into the flange initially to create a seal. You have to deform it so it flows into all the little microscopic imperfections in the metal surfaces.
Okay, so that's the initial tightening, the brute force to make it conform.
Right, but once you do that, you turn the machine on, the pipe pressurizes, the internal fluid pressure now tries to blow the flange apart. The M factor is the maintenance factor. It's a multiplier that tells you how much residual clamping pressure you need to keep on that gasket to ensure it holds against the fluid trying to escape.
So you can't just tighten it and forget it. You have to make sure the bolts maintain that clamping force, even when the system is actively fighting back.
Exactly. Now, what about O-rings? These are everywhere.
Everywhere. And the Joule effect comes back here, but in a totally different, really weird way.
This is one of my favorite counterintuitive facts in all of engineering. Rubber, when it's under tension, when it's stretched, behaves strangely. If you heat it up, it contracts.
It shrinks. Most things expand when they get hot.
But rubber, if it's stretched, contracts. It has to do with thermodynamics and entropy and polymer chains coiling up. Now imagine you take an O-ring and you stretch it over a rotating shaft to seal it.
Okay. The shaft is spinning inside the stretched O-ring.
The shaft spins, friction generates heat, the O-ring heats up. Because it's stretched, the heat makes it contract. It squeezes tighter on the shaft.
Which creates more friction.
Which creates more heat.
Yeah.
Which makes it contract even more. It's a catastrophic positive feedback loop.
A thermal runaway.
The thermal runaway of destruction. The seal fails, and it fails rapidly.
So how do you avoid that? How do you use an O-ring on a shaft?
You never, ever stretch an O-ring over a rotating part. You design the groove so the O-ring is in compression. You put the ring in a groove in the housing, and the shaft runs inside it. You squash it into the hole rather than stretching it over the shaft.
That is a life-saving tip for a designer. Wow. Now, what about dynamic seals? For when the shaft is spinning at, say, 10,000 RPM, you can't just squeeze a piece of rubber against it. It would melt.
No, it would burn up instantly. For high speeds, we have to use more sophisticated, often non-contact seals, like labyrinth seals.
Labyrinth, like a maze.
Exactly. It's a non-contact seal. You create a tortuous path for the fluid, a series of sharp teeth on the rotor and grooves in the stator. The fluid has to navigate this maze. It tries to rush through the first tiny gap, then it expands to a large chamber, it loses energy and pressure, then it tries to rush through the next gap.
That gets tired.
Effectively. At each step, at each toot, it loses pressure. By the time it gets to the other side, the pressure is negligible and the leakage is minimal.
And the source mentions that sharp corners are better here. Why is that?
Yes, sharp corners create turbulence. That turbulence dissipates the kinetic energy of the leaking fluid very effectively. You want the flow to struggle as much as possible.
Then there are brush seals. These sound like a toothbrush.
A very, very high-tech toothbrush. They are made of densely packed bristles, thousands of them, made of superalloys. They actually touch the shaft, but they're flexible, so they can bend and comply with its movement.
So they close the gap much tighter than a labyrinth seal.
Much tighter. The source says they can reduce leakage by 5 to 10 times compared to a labyrinth seal. That's a huge improvement in efficiency.
That's a massive improvement.
It is. They're standard in high-performance turbomachinery now, like jet engines.
Okay, we are holding together, running smooth, and sealing tight. But machines move, and movement creates vibration. This brings us to pillar 4, vibration and shock.
The dynamics of motion. This is where things get shaky, literally.
The sources start with the classic model that every engineering student learns, the single degree of freedom system. A mass, a spring, and a damper.
It's the simplest way to understand the world of vibration. You have mass, which represents inertia. You have stiffness, represented by the spring. And you have energy dissipation, which is the damper or dashpot.
And every system like this has a natural frequency, denoted as F-dian.
Right. It's the frequency it wants to vibrate at if you just pluck it and let it go. Depends only on the stiffness and the mass. Specifically, it's proportional to the square root of stiffness over mass.
So if you make it stiffer, the frequency goes up. If you make it heavier, the frequency goes down.
Exactly. Think of a guitar string. Tighter string, higher note. Thicker, heavier string, lower note. Same physics.
And the danger zone that everyone talks about is resonance.
Resonance is when the forcing frequency, say, the speed of your unbalanced motor, matches that natural frequency. When that happens, the system absorbs energy from the source with maximum efficiency. The amplitude of the vibration spikes, sometimes uncontrollably.
This is the opera singer shattering the wine glass. She finds the note that matches the glass's natural frequency.
That's the perfect example. The source talks about a term called transmissibility. At resonance, transmissibility spikes. The vibration coming out of the system is much, much larger than the vibration you're putting in. It amplifies.
So how do we stop it? The goal is isolation.
Isolation is the art of mismatching those frequencies. If your motor is running at 1800 RPM, you want the natural frequency of its mounting system to be much lower than that. If you can get the transmissibility below 1, you are actively isolating the vibration.
That's why we put engines on soft rubber mounts.
We're lowering the stiffness of the system, which lowers the natural frequency way below the engine's operating speed. The engine can shake, but the soft mounts prevent that shaking from getting to the car's frame.
The sources also talk about modes of vibration, with nodes and antinodes.
Right. If you vibrate something more complex, like a beam or a plate, it doesn't just move up and down, it forms a shape. There will be points that don't move at all. Those are the nodes, and points that move the most. Those are the antinodes.
And the fatigue failures we talked about way back in Pillar 1, where do they happen?
They almost always happen at the antinodes, where the bending stress is at its maximum, or at the attachment points where the vibration is being constrained. If you're inspecting a machine for cracks, that's where you look first.
Balancing is another huge topic here. The difference between static and dynamic imbalance.
Static is the simple kind. If you have a heavy spot on a tire and you put it on a frictionless axle, gravity will pull the heavy spot down to the bottom. You can balance it without even spinning it.
But dynamic imbalance is trickier.
It is. It creates a couple, a twisting force. You might have a heavy spot on one side of the tire and another heavy spot on the other side, but at the opposite end of the diameter. It's statically balanced. It won't roll to one side, but when you spin it, it will try to wobble violently. You can only detect it when the part is spinning.
The analogy of balancing a car tire is perfect. They spin it up and put little weights on the rim to counteract that mr omega squared force.
Precisely. You're trying to make the center of mass align perfectly with the center of rotation.
Now, how do we measure this vibration? The accelerometer. And I love the analogy in the source. It compares the piezoelectric crystal inside to a sponge.
It's a great visual, isn't it? A piezoelectric crystal is a material that generates an electric charge when you squeeze it. So think of it as a sponge full of electric juice. Inside the accelerometer, you have this crystal with a small mass attached to it. When the machine vibrates up and down, the inertia of that mass squeezes and releases the crystal sponge. The harder the acceleration, the harder the squeeze, and the more juice comes out. We measure the juice, the voltage, and that tells us the acceleration.
Yeah, it makes it so clear. It's brilliant. Okay, finally, noise control. Vibration makes noise.
Sound is just a compressional wave in the air created by a vibrating surface. To stop it, we look at a property called transmission loss.
And the source brings up the mass law.
The mass law is blunt force physics. Heavier is better. A heavy, massive wall stops more sound than a light, flimsy wall. It's simply harder for the sound wave's energy to physically move the heavy mass. If you want a quiet room, build thick concrete walls.
But there's a trap, a weird phenomenon called the coincidence effect.
Yes. This is where physics plays a nasty trick on you. At a certain frequency, the wavelength of the sound wave in the air can match the natural bending wavelength of the panel. When that happens, the panel becomes acoustically transparent. It vibrates in perfect sympathy with the sound wave.
So the sound goes right through.
It goes right through. The transmission loss, which should be getting better at higher frequencies, suddenly plummets. It's a form of resonance between the air and the structure.
To fix these things, we use damping. The source lists 3 types: viscous, Coulomb, and hysteresis.
Right. Viscous damping is like a dashpot. It's drag through a fluid. The force is proportional to velocity. The faster you try to move it, the more resistance you get.
Okay.
Coulomb is just dry friction, 2 things rubbing together. It provides a constant resistance force, regardless of speed. And hysteresis is internal material damping. It's the material itself absorbing energy. Think of a rubber ball. When you bounce it, it doesn't come back to the same height because some energy was lost as heat within the rubber. That's hysteresis.
So what does this all mean? We've looked at stress, lubrication, seals, and vibration. How do they all tie together?
It means that successful mechanical design is a balancing act. It's a system. You need strength from your stress analysis, but you need fluidity from good lubrication. You need containment from your seals, but you need stability from vibration control. If you optimize one tiller at the expense of the others, the whole machine fails.
It's an ecosystem. They're all interconnected.
It is. You can build the strongest engine block in the world, perfect stress analysis, but if the head gasket fails because you didn't calculate the M and Y factors correctly, or the bearing seize because you didn't account for EHL, the engine is just a very, very expensive paperweight.
It connects back to that idea of the system. A machine isn't just a collection of parts, it's an interaction of forces.
Exactly. You can't isolate them.
Before we go, I want to leave the listener with a thought. The factor of safety. We use it in all these calculations. We say the stress is X, so let's design the part to handle twice X.
Right. N equals 2 or N equals 4 for an elevator, maybe even higher.
But is the factor of safety just a factor of ignorance? As we get better at understanding these four pillars, as our math gets more precise, our simulations more powerful, can we start to reduce that safety factor? Can we make machines lighter, more efficient, push them closer to the theoretical edge? Or does the chaos of the real world, the pothole you didn't see, the bad batch of oil, the operator error, always demand that margin for error?
That is the eternal question of engineering, isn't it? It's the constant tension between optimization and robustness. How much do you trust your math versus how much do you fear the unknown?
Something to mull over.
Yeah.
Thank you for diving deep with us today. This was fantastic.
My pleasure. It was a lot of fun.
And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.